Mark your calendars.
All right, perfect. All right, I think it's time. Welcome back. I want to do some more examples of these proofs of convergence, and then we'll move on to something else, I think, if we have time. At the very end last time, we did a somewhat fancier than usual example, and I want to try some more that are like that. And the moral of the story, I don't know if you remember this, is when simplifying, we can use equal or less than. This was the basis of that trick. In this step, in the part of the proof when you are simplifying, you can simplify using the equal sign, which is what all the ones we've done so far were like that. But if you want to, you can also use the less than sign, and everything will still work out properly. All right, so I wanted to try one like that, and then I have some for you to try like that. How about this? This converges. Can anybody say? So first, before we do it, you have to know what it converges to. Yeah? 2/3. 2/3, yeah. How do you know that?
If they n squared both get really big.
Yeah, when you have a fraction involving polynomials, if like the degrees on top and bottom are equal, then the thing converges to this ratio of the coefficients in front of the top degree terms. I hope you remember this little trick from calculus. All right, so it does converge to 2/3. Let's see if we can actually prove it. All right, we always begin in the same way. Let epsilon greater than 0 be given. We will find some n, an actual number, such that n greater than the big N implies absolute value. And then remember, I hope you all remember this. You know, you're going to end up writing this so many times. I said you need to memorize the definition, but hopefully you're going to write it so many times that you will just naturally remember it after a while. Inside an absolute value sign, I want to see an minus a, which is the limit. So this is somewhat complicated, but it is. An is the sequence term with n's in it, over 3n squared minus 1, like that, and then minus the limit, 2/3. And we need to show that being less than epsilon. All right. So I am going to do my little sort of work on the side here, which is where most of the work happens, really. And I'm going to take that thing inside the absolute values and try to simplify as much as I can. Eventually sort of set it equal to epsilon and solve for n. Well, set it less than epsilon and solve for n, saying n greater than whatever. But anyway, let's see if we can simplify here. Anyone want to suggest how can we simplify that? There's a very non-straight line there. Anyone know what this is called? This is my little mathematics trivia. There's a name for that bar. It's called the vinculum. Look it up. Anyway, what should I do with that? Yeah, you got to make a common denominator. This is a typical trick that you're going to use. If the sequence involves fractions, you should expect to have to combine it using common denominators. And I guess the common denominator is going to be 3 times 3n squared minus 1. You could probably try and do it in a fancier way, but that's the simplest way. So my denominator will be 3 times 3n squared minus 1. So in the first term, I multiply by 3. I'll just write it out. 2n squared plus 7n minus 1, like that. And then minus the second part is 2 times 3n squared minus 1 over 3 times 3n squared minus 1. All right, and then, distribute on top and recombine the terms. It looks like I'm distributing the 3 on the first one, 6n squared plus 21n minus 3. And then subtracting, I'm just putting them all over the same denominator here. 2 times 3n squared gives me negative 6n squared, and then 2 times negative 1 is a negative 2, but I have another negative, so that should be a plus 2. I think I'm doing that right. Distribute the minus sign. Yeah? Did I mess it up? 6n squared, yeah, thank you. You got the squared. Okay, and now let's combine terms in the numerator, I guess. Pretty soon I'm going to have to actually do an interesting step, but not yet. 6n squared cancels with negative 6n squared. 21n, I guess, stays like it is. Minus 3 and plus 2 is minus 1. And then maybe I'll distribute the 3 on the bottom. That doesn't matter so much, but might as well. All right. That says 21n. It looks like 2 times the natural log. It's not. It don't make no sense. I try to tell my calculus students that. Sometimes I see people like ln x over x. They're like, oh yeah, I just cancel the x's. I get log. No. I say, what? Log. Log by itself is not a thing. You all know that. None of you would ever write that. Okay, so this is 21n. Maybe I'll space it out a little. 21n minus 1. Okay, what can we do next? Now is the time when you actually have to have some kind of minimal idea. Actually, can we first talk about the absolute value signs? There's usually a step during which I say, okay, now I can get rid of the absolute value signs because everything is positive. Even if some parts are negative, if you know they're negative, then you can take the absolute value and make it positive. Are these things positive on the top and the bottom? I think actually they both are positive on the top and bottom. Since n is a natural number, like 1 or greater, then the top and the bottom both are positive. So at this point, I can get rid of the absolute value signs. I haven't really done anything too fancy yet because I'm just using equal signs every time. But now is the point at which I'm going to start using less than signs. And the reason, like, this by itself is not appropriate to finish, because remember, what you do at the end, don't write this down because I'm going to just erase it again, is you put less than epsilon and then you try to solve that for n. But this is too complicated to solve for n in an inequality like that, because I have n squareds and also n's. If there was just an n squared, you could probably do it by taking a square root. If there was just an n, it would work out fine. But n squared and an n in there at the same time, it's no good. I don't like these constants much either, but I don't know what are you going to do about that. I don't know if you remember the example we did last time, but I used a less than sign. There's a few things I can do here, but one that's a simple thing to do is I can just ignore this minus 1. I'm trying to make the thing bigger over here. I can just omit the minus 1 on top. Right? I just made the fraction bigger, so that is a legal step. I'm going to try to, I don't know how this is going to work on your paper, but I'm going to try and summarize some typical less than tricks. Less than tricks. I just did one of them, and that is throw away a negative constant in the numerator. Often you'll get to this step and you just won't know what to do next to simplify it. But I'm going to try and summarize it. Typical tricks that you would do here, using a less than sign. One of them is you can throw away a negative constant in the numerator. That's what I just did. And that makes the thing bigger. And that will usually help a little bit to simplify, although I have bigger problems than that here. This also, can I just say, for the same reasons, you can also throw away a positive constant in the denominator. This makes the denominator smaller, which has the effect of making the whole fraction bigger. All right, so these two tricks can kind of go together. You can throw away a negative constant in the numerator, which makes the whole thing bigger, or you can throw away a positive constant from the denominator, which makes the whole thing bigger. All right. Unfortunately, I have a negative constant in the denominator, so it's not legal to just erase that, because actually then the inequality would go the wrong way around. You will have made the fraction smaller rather than bigger. So you can't just omit that. Here's another typical trick, though. You can change a positive constant, with two n's in constant, in numerator, two n's. What I mean by that is if you have something like 3n squared plus 4, you can change it to this. This looks a little weird, but first of all, I hope you agree, it's definitely legal because this is definitely bigger than that. I changed the 4 to a 4n squared. What's the point of changing it to a 4n squared? Well, then I can actually combine the terms together and then hopefully maybe cancel something out somewhere else, all right? So you can change a positive constant in the numerator to some power of n's, which then you will combine with something else. Or, similarly, in the denominator, if it's negative, you can do this. So, and this is actually what I'm going to do in the current example that we're doing. You can change a negative constant in the denominator to some power of n's. And this is the trick that I'm about to do in our present example. All right? For the same reason, that ends up making the fraction bigger. So, this is the next trick I'm going to do. From here, this thing, start it over here. This is now less than, I am changing the 3 downstairs to a minus 3n squared. The reason I did that is so that now I can combine those two terms and then you can cancel n's on the top and the bottom. This is 21 times n on top, and it's going to be 6n squared on the bottom, and then we'll really cancel it. So this is 21n over 6n squared. Cancel the n's, I get 21 over 6n. And that, I like the looks of that. Because, simplify the fraction? Yeah, all right. You want to be fancy about it? All right. 7 over 2n, right? No. I did this whole problem on my paper not realizing that I can simplify the fraction. Yeah, it doesn't matter, but you might as well. All right. Remember where we intend to go with this is put less than epsilon, and then you solve that little thing for n. So I'm going to say I'm almost done with my sidebar here. We need 7 over 2n to be less than epsilon. So this is the same if I rearrange some things. N greater than 7 over 2 epsilon, right? Multiply the n onto the other side and then divide the epsilon back onto the other side. This right here is what we're going to use when we proceed with the actual proof. All right? What I'm trying to demonstrate and what's different about this example from before is just these weird tricks. Throwing away the minus 1 here and then changing this minus 3 to a minus 3n squared. Those are some typical less than tricks that you will want to use when you're doing examples like this. Yeah?
Why that works? Like why you put in the n squared?
Yeah, so this, you think of what I'm changing here is I'm changing it used to be a 3, and I'm changing it into 3n squared. Now this was subtracted, so here I'm subtracting even more than I used to be, right? It used to be you're subtracting 3, now I'm subtracting more, which means I made the denominator smaller, which means this whole fraction is now bigger.
Okay.
It's kind of complicated, and people who are really good at real analysis are really good at looking at things like this and knowing instantly, oh yeah, I change this and it makes it bigger. I consider, if I'm speaking honestly to other mathematicians like you all, I don't consider myself to be all that good at real analysis. I mean, I know all the theorems and whatever, but I always have to think very carefully when I do these kinds of tricks, because I always am worried about doing it the wrong way around. If you do it the wrong way around, well, you get the wrong answer. All right. Okay, can we proceed with the rest of the proof then? This really was just my little sidebar calculation to determine what the big N should be. So the rest of my proof continues from there. Sorry, I have to scroll. Let the big N be some natural number greater than what I end up with, 7 over 2 epsilon. right, then if n is greater than the big N, we have, and now I have to write out my original thing inside the absolute value signs, 2n squared plus 7n minus 1 over 3n squared minus 1 minus 2/3, right? This. And now you can write in the simplifications, or you can just say, I mean, I already wrote them all down up here. I start with this. This is equal, 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 less than, equal, equal. Eventually it's less than that, 7 over 2n. So this is less than 7 over 2n. All right. Pulling this out of nowhere, it looks crazy, although it is true. That is less than 7 over 2n. And then here, we just do the usual thing. I've changed the little n to a big N, changed the big N to a, whatever it says there, 7 over 2 epsilon. So this is 7 over 2 times 7 over 2 epsilon. And then those little 2's will cancel, the 7's will cancel, and you end up with 1 over epsilon, which is epsilon as desired. All right. That's how it's done. Any questions about that? I have a couple examples for you to try. Actually, something that I like to do in this class is I got out my recent copies of the Fairfield University Mathematics Comprehensive Exam. I'm sure you've all heard of this. This is something that all seniors have to take in your senior year. I know that describes some of you. And last year's exam featured a problem much like this. It just said, here's the sequence, you should prove that the limit is whatever. And you do exactly this thing. I decided, oh yeah, I'm gonna have them, let's do that real comprehensive exam problem in class. But it was too easy. It was easier than this. It was, so I don't think we really need to do this one. But the comp question said, show that this converges to 1. This actually, we did something very much like that last time. Maybe exactly that or just a simple variation. So I hope you can feel accomplished, that you know how to do at least one question on last year's real analysis comprehensive exam. There were some questions just about soups and imps that you also could have done, which I forgot. I forgot until today. I thought, oh man, I should have brought out those old questions a few days ago, but I forgot to look at them. Anyway, I would like you to try. So both of these examples involve doing some of these little tricks that I was just talking about. Here's one that's very much like the one that I just did. I'll let you think. So first of all, think about what is the limit? What does it actually converge to? And then actually show that it converges to that. And then this second one is quite strange, but it turns out to be not much harder. N plus sine of n. Can you believe it? Sine of n over 2n. See what you think. Actually, maybe, can we talk about this one? What does this one converge to? Do you have an idea? 1/2. Yeah, why did you say that?
Because there's an n and then 2n on the bottom, so 1 over 2.
Okay, what about this though?
I don't know, it's always thought that if there's like the n, like if it's the same power, you like
Right.
disregard everything else.
Yes. Well, that is true of polynomials. If you mix it with other functions, then weird things can happen. Like, for example, if it was n plus e to the n over 2n. The reason you disregard other things in a polynomial is because this one is the biggest. Like here, this n squared is bigger than the other parts. But in this, you would get the wrong answer. Ignore this part because that's actually bigger. Anybody have a feeling about the sign n here? Yeah?
Isn't it just an open, like with 1 and 1, and then when n gets really large, it's going to be.
Yeah, right. So actually what you said is correct. This part doesn't matter because the n, when the n is really big, the n is really big, but sine of n is never really big. It's just between -1 and 1. And so, so the sine n is basically irrelevant here, and therefore what you get is 1/2. She was right. This will be important though in your proof. The fact that the sign of n just goes back and forth from -1 to 1, that is relevant, which is why I wanted to mention it before you all tried it. All right, I'll give you some time. I'm going to walk around and see how you feel. Your first job is to decide what that first one converges to. I'm going to make a modification to something I said up here. I said these things throw away constants. I mean, it's not wrong what I said, but actually you can throw away really any. Can I change this to term? It doesn't have to be a constant that you get rid of. It can be anything really, as long as it's negative, right? That's the point. You're trying to make the thing bigger. This may be helpful. I don't know if it matters. All right.
That's pretty good.
If you take away the n squared, it's
Yeah. And then just take away the positive one too. Still be gonna be one.
Oh, yeah.
No.
Alright.
Could we just cover this? This? That's the bigger.
Throw it positive.
Just left and that negative.
Through.
Okay, what's it?
Make the denominator. Yeah, you can't make it negative.
What about for that?
Don't try to.
Don't try to
leave
find it.
this in there. You can throw it away.
Okay.
You can't throw it a plus one.
Okay.
Maybe that's why I wrote it. No, you don't throw it so much that it
So I just confused all the
yeah.
because the numbers are natural numbers. One, two, three. Well, you could just make this as six. You can factor it in and cancel it. Where you can.
Or you can give it numerator heads. You can give the 5 and then
Why don't we give it a red color?
oh yeah.
Six ten.
So now we have this is we keep it a little cleaner.
Yeah.
This is ready.
Okay, so, like, I would.
Yeah, that's the typical thing that I would do to handle this.
Okay.
Six seven squared.
Yes, okay.
What is that? And it's good.
Yeah, the key step. So you can say, well,
So I would just, yeah, so that,
yeah, just have to know and now you can do a less than. Change this. Just said.
yeah.
I would replace the top with something that you know is definitely bigger than
Like any number bigger.
yeah, because you want to make this fraction. Or greater or equal.
So just get rid of like,
Yeah, yeah. Yeah, but it's the point is sign is less than. That's right, sign or your
How is 6 bigger than every, like, if you do it, like, what if n was 500?
Then that you can compare. Do like a less than, so that choose 6 squared minus n.
We can just get rid of the 1 minus 1.
What they were saying before about sign is down to
Oh, it's not good.
yeah, that's the value. I was supposed to for less than
Also made this
All right, I think I'm ready to talk about these. I know not everybody's done yet, and that's fine. For the first one, I started it off a little bit. Would you mind if I just write sort of the middle portion, which is really what I'm trying to talk about here, is the simplifying business in the middle. So this one, for the first one, what I did so far was, first of all, I just threw away the absolute values, because you can tell from the outset that the numerator and denominator here are both positive. And so it's like this. Now, some of you realize, I think, there's like a lot of, you may feel like some kind of creativity paralysis. It's not clear exactly what you should do from one step to the next. And there are many, many things that you could do. For instance, nobody did this, but you could have, from there, you could have said less than n plus 500 over 2n squared minus n plus 1. That's true. I changed the 5 to a 500, which is bigger. Are you allowed to do that? Sure. Should you do that? Probably not. There's many things that you could do, and part of what makes it tricky is knowing what's going to actually work in the end. And as I was walking around, I saw several people doing things which were not wrong really, but just not good for anything. What I did was I like n plus 5, I want to actually try to add them up into a single term. And so I changed the 5 to a 5n, and then they can add up to give me 6n. And on the bottom, I omitted this plus 1 here, so that it's 2n squared minus n. The purpose of that is now I can factor n out of the bottom and cancel the n's. And then the whole thing will have only one n left in it. Yeah?
I guess the question is just like, if you can just cancel it to make it like bigger, why can't you just cancel the entire bottom of the bracket? As in,
Yeah, this is a great point. Sometimes you will do things that are technically correct, but screw up the entire thing later on. So actually, yeah, maybe I'll just try what she just said. So don't write this down because this is well, it's not exactly wrong, but it's a bad idea. How about just do that, because certainly this is bigger than that, because I just threw away the denominator entirely. But remember, what has to happen at the end is I say something like I would proceed the very end by saying this: we need 6n less than epsilon, and then solve for n less than epsilon over 6. And this is no good because the rest of the proof needs to say let n be greater than something. And the inequality is the wrong way around here. And you will not be able to make the rest of the proof work. That's the problem. So this, what you did here, each of these steps, you're kind of like giving away a little bit of precision. Like when you're using the equal sign, these things really are equal. Here, I'm making a little, I'm fudging a little something. I'm changing the 5 into a 5n. You have to do your fudgies in such a way that you don't totally ruin the main feature of this is that the power on the bottom is bigger. And that's what makes it so that the limit is 0 in the first place. So as you're doing these inequalities, you better do it in such a way that the power on the bottom stays bigger in every step, or else you're going to mess up the basic feature of the convergence. So yeah, not everything which is permissible is actually beneficial, right? Isn't that in the Bible somewhere? Somewhere. It's in the Jurassic Park. Get them confused sometimes.
Is a helpful way to think of that maybe like when you take like a limit, where you're like doing this kind of think about what beats it at limit?
Yeah, like in a sense, this thing, its limit is 0. It better be 0 all the way throughout this whole process, or else you probably messed it up somewhere. Yeah. So what I'm going to do, what I'm actually going to do, and there are different ways to do it, but I'm going to, like I said, factor the n out and cancel, so it becomes 6 over 2n minus 1. And now that I make less than epsilon. 6 over 2n minus 1 less than epsilon, and we solve for n here. So multiply that over, divide the epsilon. Can't do that all in my head. Divide the epsilon, add 1, and then divide everything by 2. Something like this. I don't know. I didn't see anyone write that. But is that? I divided the epsilon first, and then I added 1, and then I divided by 2. You like that? Did you solve it? Did you distribute the epsilon first? Maybe.
I don't know.
What did you
Oh
get?
yeah, so did I, because I changed the negative 1 to
I don't know.
an n.
That's like ugly to me.
You
So
changed
that-
the negative 1 to an n. Okay, yeah, actually that's even better. Then it's easier that way.
Okay, yeah.
Everybody wants to do it that way? All right.
So that's just-
Okay, let's do it that way then. All right, so this, yeah, that's better. 2n minus n, right? I made the denominator smaller. Yeah, that should work. This is 6 over n. Yes, much simpler. Isn't that a relief? There are many ways you can do this. Yeah. All right. Everyone satisfied with this answer? Great. Sorry, I gave a worse answer. Not incorrect, but just not as nice. All right. And then I'll leave it to you to write. The rest of the proof goes around this basic skeleton, right? Can we talk about the other one? N plus sine n over 2n. So you begin with this, n plus sine n over 2n, and then minus a half. You decide ahead of time that the limit is a half. I don't know if anyone ever wondered, what if I picked the wrong number here, but still made the rest of the proof work out? Should be worried about that. Could you prove that this converges to anything? If you just like, I mean, if instead of 0 here I had like a minus 1 or something, could I still do the simplifications and make everything work? The answer is it's just not going to work. There's a certain amount of magic that has to happen in order for you to do this at all, and it's just not going to happen if you chose the wrong value for the limit. You're not going to be able to make this look anything like that. Anyway, let's just see if we can do this one. So here, again, we'll make a common denominator. The common denominator will be 2n. That's what it has to be. So this is n plus sine n over 2n. I got to multiply by 2 the first one, and then multiply by n the second one. Then subtract. I get 2n plus 2 sine n. I left out an n. Minus n over.
How did you multiply it by 2?
I should not have multiplied it by 2. Sorry. Yes, I already have the right denominator on the first one. Yeah, thank you. No 2's. Good so far? All right. Now we cancel the ends. All of this is routine until this point right here is when you stop and say, I don't know what to do next. One little sort of half step that you can do next is you can actually do the absolute value on the top and on the bottom. The bottom is positive, and so the bottom can stay like it is. The absolute values really only matter on the top. And now you have to have an actual real idea. And the idea here, which as I was going around, I saw most people settled on this eventually. Sine of n, as we know, it just goes, its value is only between -1 and +1. And so I can use a less than, I suppose it should be a less than or equal 1 on top. Because sine of n in absolute value is less than 1. That's the whole trick. And now this, you can easily do your thing with the epsilon, and so I say 1 over 2n less than epsilon, solve for n. N is greater than 1 over 2 epsilon, and that's the n you have to use. Yes?
So that's kind of like you for everyone. Should we make it 2 instead of 1? 2 is greater than 9.
Sure. Yes. That would still work. Or I could do, 10 here. Then this would be a 10. Then this would be a 10 here. And it would still work. Because all this, making that sort of silly change for no reason, all it does is it ends up making the n bigger. But the whole point of the proof is that the n is like really, really big anyway. So I just made it 10 times bigger, which doesn't make a difference. All right. Another thing that I saw some people do, just to, like from here, just to make it even simpler, and I usually wouldn't do this, but you can. I can get rid of the 2 on the bottom, because that's even bigger, right? And then the rest of the proof will still work. Then I say 1 over n less than epsilon, and greater than 1 over epsilon, instead of 1 over 2 epsilon, which is what I said before. And this will still work, the rest of the proof.
So why are you able to get rid of the equals and the greater than bigger? Does it just still matter? It's still bigger?
It doesn't matter, because when you eventually do this, like in the prestige, right here, all of this stuff is going to be, some of them will be less thans. If one of those is a less than or equal, the whole thing across is still a less than overall. So yeah, you can use less than or equals if you want. Although if you really want to stick with strict less thans, you could just change that to a 2 instead of a 1. Or maybe you wanted to make this a 2 so that it would cancel the 2 on the bottom. Whatever. There are many, many things you can do that will work.